Hi there, students. Today we're going to be continuing the Blitzer text for section 2.1, the addition property of equality. So what we're going to be doing now is learning how to solve linear equations in one variable and everything that goes with that. So why don't you go ahead and pause the movie and do the warm-up. Okay, let's see how you did. Um, Remember that when looking at this first problem, we've got subtraction, but we've also got division in there as we're moving from left to right. So the division is going to come first. So here we go. Let's see how you did. Oops. This is going to be 1/2 minus 2/3. And remember, we can flip that divisor and change it to multiplication. And the plus 3/10 will go along for the ride. So this statement here is equivalent to this here. And then next up, we will have 1/2 minus, so we can divide out a 3 from each of these, and at the end of the day, we will get minus 2 times 3 is 6, and 1 times 5 is 5, and then plus 3/10. Now we've got three fractions that we're adding and subtracting, or subtracting and adding actually. So the least common denominator is going to be 10. So if we multiply this guy by 5/5 and this guy by 2/2, remember you're allowed to multiply anything by 1 and it won't change the value. What we will get is we'll end up with 5/10 minus 12/10 plus 3/10. We didn't have to alter that guy at all. And then this will give us 5 minus 12 is -7. So we'll have -7 plus 3. I'm going to go ahead and put that all over our 10. So the -7 came from combining the 5/10 minus the 12/10. And then we'll have a -4/10. And we can go ahead and reduce that. 2 divides both of these. 2 goes into 4 twice and into 10 5 times. So we'll end up with -2/5. And we're done. Okay. All right, and the second warm-up, we've got division and multiplication. They're on the same hierarchy. So what we need to do here with this guy is move from left to right. So -40 divided by 5 gives us -8. So this here had this result. And then the times 2 goes along for the ride. So at the end of the day, we will get -16. Now, if you ever have trouble where this is kind of one of those sucker problems where a person often wants to put imaginary parentheses around the 5 times 2. So if you ended up with, I guess that would have ended up with -4. What you could have done is change the whole thing into multiplication. If you did -40 times 1/5 times 2, then I think that helps to reduce that error. Right? So anyway, we'll put our happy box around this guy and move. All right, so linear equations in one variable. In chapter 1, we learned that an equation is a statement that two algebraic expressions are equal. We determine whether a given number is an equation's solution by substituting that number for each occurrence of the variable. When the substitution resulted in a true statement, that number was a solution. When the substituted number resulted in a false statement, that number was not a solution. Okay, so a little bit of vocabulary. Solving an equation, the process of finding the number, or sometimes it's more than one number, so we can say numbers, that make the equation a true statement. These numbers are called the solutions or roots of the equation, and we say that they satisfy the equation. So now we come to another definition here, a definition of a linear equation in one variable. So a linear equation in one variable, and often we use x, it's first, to get you broken in kinda, is an equation that can be written in the form a times x plus b is equal to c. Now don't be nervous. We know that a, b, and c are real numbers, so they'll be something that you know. And we don't want a to be equal to 0, because if that was the case, we would just have constants, right, instead of variables. Okay, so why don't you think of 3 examples of a linear equation in one variable, and let's see what you got. So go ahead and pause the movie, write down 3 examples, and see if they're similar to anything I put down. All right, let's see how you did. One example could be maybe 2x plus 5 equals 1/2. So your A would be 2, your B would be positive 5, and your C would be 1/2. We could also have something like, I don't know, negative x over 3 plus 8 equals negative 1. So what would our A be this time? Good, it would be negative 1/3, right? Because negative 1/3 times x over 1 would be negative x over 3. Sometimes those get a little tricky. And couldn't we have something like 12x equals 5? What would my b, what number would b take on in that case? Good, b would be 0 in that case. All right, so moving right along. Now, let's give 2 examples of a nonlinear equation in one variable. Nonlinear equation in one variable. What do you think? Let's see. Okay, so if I had the square root of x was equal to some number, call it 2, that would be linear because that is the square root of x, not x to the 1 power. You'll find out later that the square root of x really means x raised to the 1/2 power. Okay, another example could be, well, we could do 3 over x plus 2 equals 5 because x is in the denominator now, so that would not be linear. And there's many more examples, so you can always email me and ask if yours worked out. Okay. Equivalent equations. Equations that have the same solution are equivalent equations. The addition property of equality says that the same real number or algebraic expression may be added to both sides of an equation without changing the equation's solution. So that is if A is equal to B, then A plus C has to be equal to B plus C. Now, C could be a negative number, so a lot of times you might be thinking, oh, what about subtracting the same number from both sides? That's equivalent to this because it's adding the opposite. Right? Okay, so go ahead. Well, let's do the first example together. And, one thing that you might want to consider, I know that you've had algebra before probably at some point in your math life, but, you're back here in beginning algebra for a reason. So you might try showing all the steps, work on keeping your steps very organized. All right, the equal sign should stay in the middle each time. All right, and let's see what's going on. So in this case, our goal is, in order to solve, we want to isolate the variable. In the case of number 1, the variable is y. So how would we isolate y? Good, we would add 5 to both sides. So we have to add 5 here. And in order to balance that out, we need to add 5 to the other side. Okay? So what I showed you here is using this property by adding vertically. I'm going to do one more example after this where it looks just like the property above where we're adding horizontally. So here we go. We'll get y plus 0, because negative 5 plus 5 is 0, is equal to negative 13. Well, y plus 0 is just y, so y is equal to negative 13. Now you would want to check that in the equation. Negative 13, if I plug that in for y, minus 5, is that equal to negative 18? Yep, it sure is. So you got the right answer. And that's what you should do for every problem, either mentally or written. So here, we want to use roster notation. Roster notation. What this says is that negative 13 and only negative 13 will work as the solution to that equation. All right? Good. All right, so let's take a look at number 2. With number 2, what we need to do here is we need to isolate the z. So here, do you see that? Let's leave the 18 and then we'll leave a space and have the plus z is equal to 14. So we need to add a negative 18 to both sides. Now if you want, you can just subtract the 18 from both sides, whatever works best for you. Now 18 plus negative 18 gives us 0, plus z is equal to negative 4. Now 0 plus z gives us a result of z, so z is negative 4. Again, our roster notation, we get negative 4, and you're all done. So go ahead and pause the movie and try the rest of these problems and see how you do. I don't mind which way you do it. I usually work vertically, but if you'd rather work horizontally, that's just fine. Good luck. Okay, we're back. We're back. We are going to see how you did on the rest of these problems. So for this next one, we need to we're going to be subtracting 10.6 from both sides of the equation. Okay, so on the left side, you see that we'll get x plus 0 is equal to, now the 9 is negative and the 10.6 is negative. So we'll end up with negative 19.6 on the right side. So x plus 0 is just x, is negative 19.6. So our final result is negative 19.6. How'd you do? All right. So here we go. Next up, number 4. We will be adding 1/8 to both sides. Now be careful. You've got a fraction on the right side, two fractions that have unlike denominators. So here on the left side, we're going to end up getting 0 plus x is equal to. Now I'm going to go ahead and do a little work here. Do you see that 8 is the least common denominator? So we need to balance out that negative 1/4 by multiplying by 2 over 2. And the 1/8 is fine because it's it represents the least common denominator. So now what we will get is negative 2/8 plus 1/8. So I'm going to move to horizontal right now. So this here became the negative 2/8. And then coming up here, we will have x is equal to negative 1/8. So we'll put that in. What's that notation called? Good, roster notation. Alrighty. Now we have a few things going on in number 5. We need to combine like terms. Do you see that the negative 3x and the positive 4x are like terms? So let's take care of that first of all. Do you see that's going to give us 1x minus 5 is equal to 9? Now if I add 5 to both sides, I will have 1x is just x plus 0 is equal to 14, and x is equal to 14. So you guys will have to email me and let me know which way you prefer. If you prefer doing the horizontal adjustments or the vertical adjustments. And then number 6. Got a few issues here. What do you think we ought to take care of first? Good. I think we should use the distributive law. And by the way, the negative 3x and the 4x became the 1x right here. So for this guy, I think we ought to use the distributive law here first off and get that cleared up. So 7x plus 3 is equal to 6 times x minus 6 times 1. And then we have the plus 9 still hanging out. So the yellows are equivalent here. Now we'll have 7x's plus 3 is equal to 6x's minus 6 plus 9. Then we'll have 7x plus 3 equals 6x. Negative 6 plus 9 gives us a positive 3. I'll bring us up here. Now, we'll go ahead and if I go ahead and subtract 3 from both sides, I will end up with 7x plus 0 is equal to 6x plus 0, which gives us 7x equals 6x. Now don't be worried. we have like terms, so let's just subtract 6x from both sides. And then we will get 1x is equal to 0 x's, which just gives us x is 0. So in our roster notation for our final result, we'll get 0. Now that means that 0 is the only number that will yield a true statement in that equation. Right? All right, good. Now we've already had a preview of this. We adding and subtracting variable terms on both sides. We did that with that last example. So let's make it official. Our goal is to isolate all the variable terms on one side of the equation. This is when we have, a linear equation and one variable. We can use the addition property of equality to do this. And as I said, we just did an example, and I'm going to say C. I'm just going to say C example 3, number 6. All right, so here's our application for this section. The cost C of an item, which is the price paid by the retailer, plus the markup M on that item, which would be the retailer's profit, equals the selling price S of the item. The formula is C plus M equals S. So we have the selling price of a television is $650. If the cost to the retailer for the television is $520, find the markup. Okay. So let's figure out what we have going on. So remember, we have C. Now C was the cost of the item that was paid by the retailer. Do we know that? Good. The C was $520. So we'll leave the units out for right now and just put the 520. So this is my C. Now we need to find the markup. So we'll just put plus M. And then the selling price S was $650. So this was S. So to solve this, we would subtract 520 from both sides of the equation. This would yield a result of 0 plus M is equal to $130. 0 plus M is M. And then let's put our answer in words. The markup is $130. All right. Now this next one's a little bit of a thinker problem. Whoops. Sorry, lost it there. What is the difference between solving an equation such as 5y plus 3 minus 4y minus 8 equals 6 plus 9, and simplifying an algebraic expression such as 5y plus 3 minus 4y minus 8? What do you think? Good. One way to answer this, or to think about this, is in an algebraic expression, we will not be able to solve for the variable. You could simplify, but you won't be able to solve. Okay. All right, so that wraps up section 2.1, the start of chapter 2. So now I would recommend going and doing your homework for 2.1 and have a fabulous day.